Welcome to Higher Structure Seminar Series of Feza Center for Physics and Mathematics. Today our speaker is Vassily Olegovich Manturov from Moscow Institute of Physics and Technology. And Vassily Olegovich will tell us about 10 years of GK and towards invariants of knots and links. Please.
Hmm. Okay, thank you very much. Çok teşekkür ederim. Ben çok memnun oldum burada Türkiye'de düğüm teorisi hakkında, matematik hakkında konuşmak için ben çok teşekkür ederim. So today I'm going to talk about 10 years of GNK towards invariance of knots and links. A bit more than 10 years ago, I introduced a series of groups, G and K, and formulated a very important principle which works in low-dimensional topology, and actually not only in low-dimensional topology. And today I will talk about various relations of those groups with topology, geometry, algebra, combinatorics, and many other areas of mathematics. Okay, so let me proceed. Several years ago, we published a book. The book is called Invariants and Pictures, and my co-authors are Igor Nikonov and Denis Fedoseev and Kim San-John, my co-authors, collaborators, and Kim San-John was my student. And actually, that book um, uh, had a goal to construct invariants of various objects, mostly coming from topology, valued not in numbers, not in polynomials, but it's something like pictures. And this book is about low-dimensional topology and combinatorial group theory. And the groups we will be mostly talking about today will be fundamental groups of various configuration spaces. First of all, braid groups. And of course, we have close ties with low-dimensional topology, group theory, and combinatorics. And actually, it's known that braid groups are related to some higher homotopy theory. It's known that homotopy groups of higher dimension of spheres can be described in terms of something in braid groups. And it looks likely that the construction of groups G and K works in algebraic geometry, and I will tell how. And actually, there will be lots of problems here. And today we will mostly talk about braids, but then we will try to pass to links and then maybe to knots. And mm, Actually, I just remind something that probably everybody knows. What is a braid? So if we have endpoints in R2, then a braid is a collection of n distinct non-intersecting paths. So we have some points on the top and some points on the bottom. Uh, and we have a motion of points, some dynamical system, and points should never coincide, so the path should not be non-intersecting. And the points on the top and the should coincide with the points on the bottom. Uh, Actually, we may say differently that um, the braid group, of course, braids can be concatenated, and the braids form a group. So the braid group is the fundamental group of the configuration space. So we may say that we have the configuration space of n distinct points on the top, and we look at the fundamental group of this space. Well, usually, one remark, usually people draw braids with points, with top points on a line and bottom points on a line. But we use slightly unorthodox conjectures so that we put them not on the line, but maybe on, we distribute them on a circle, then you will see why. And among braids, there are pure braids, those which connect points where each point goes to itself. Okay, so that the permutation is trivial. And now the fundamental principle. This is what the theory started with, and this is just a principle. And from now on, we will be deciphering this principle and proving theorems, formulating conjectures, and doing many other things. So here it is, about 10 years ago. So if we have dynamical systems describing the motion of n particles, and those dynamical systems possess some nice codimension 1 property, which is governed exactly by k particles. Exactly by k means it cannot depend on k minus 1, but exactly by k. On k, then these dynamical systems admit a topological invariant valued in G and K. And during the talk, I will be telling you what a nice property, a nice codimension 1 property mean, what it means exactly by K particles, what I can mean by a particle, and of course, in some minutes, I will give the definition of those groups and tell you why these groups are interesting, why we should study them, and many other things. Okay, and now here we have two pictures. So for points on the plane, which mm, are our main, 4 points on the plane, which are our main hero and our main example for braids, for describing braids. The first property is 3 points are collinear. And the second point, the second nice property is 4 points are on the same circle or line, maybe. So you see, this is these two properties are both of codimension 1. So generically, no 3 points are collinear. In general position, no 4 points are on a circle. But if we do some dynamics, then generically there will be finitely many moments when 3 points are collinear or 4 points are on the circle. So this is what I mean by codimension 1. Okay. And so here is an example. If we have a braid in 3 space and move points, maybe I can call them 1, 2, 3, 4. I can look at those moments when 3 points are collinear, for example. And I will write a word. A word will be in generators, and generators will have indices, and those indices will correspond to those points which are collinear. So for example, here 1, 2, 3 are collinear, and here 1 to 4 are collinear. So having this situation, I will write down the word A1 to 3, A1 to 4. Okay, so this is how I write a word from a braid. And now the main definition. The main definition of groups G and K, actually, I don't know whether this notation is used in Turkey, but this is a notation very much used in France and in Russia. So C and K is choose NK. So the number of choices of NK. So in English-speaking countries, it's usually denoted by that. And the notation comes from choose NK. Okay? So this is a group which has that many generators. Yes, A1 to 3 is the same as 3 to 1. Right. So the group G and K is defined by generators called AM, where M is an index and M is uh, K element is a K element set from 1 to M. Uh, um, so there are choose NK possible generators, so unordered sets. And we have three types of relations. So first, all my generators are involutions. So each generator squared is 1. So this makes um, mm, my group similar to Coxeter groups, and actually they are related to Coxeter groups, and this is important. Then the second relation is the far commutativity relation. If two sets of indices, M and M prime, have intersection which is not maximal possible, then these generators commute. What does it mean, not maximal possible? We have k element sets. So their intersection can have cardinality k minus 1. So if it's not the case, then the generators commute. The second relation never happens for gk plus 1k. And that's why for gk plus 1k, actually many things are easy to work with. So word problem and some other things. But this makes our groups very similar to break groups. You will see why. And also, the most interesting and the most important relation is as follows. So assume we have some k plus 1 tuple of distinct indices u1, k plus 1. Then we can choose. Uh, some k of them. And so there are k plus 1 possibilities, and write down indices like this. M1, M2, and Mk plus 1. So then this product in this direction is equal to the same product in the opposite direction. So since all those are involutions, we can just write that this element squared equals 1. Well, actually, if we take a G and 2, then my generators can be called Aij. And then the third relation looks like Aij, Aik, Ajk equals Ajk, Aik, Aij. And actually, people working with Young-Baxter can easily recognize that this is a group-like version of the Young-Baxter relation. And the second relation actually means that if we have four distinct indices, Aij, Akl, then this is the same as Akl, Aij. And actually, you may imagine that we have something like strands, and the second relation means that independent events commute. So if we have, say, strands ij and kl, then independent events commute. And here we have something like the third Reidemeister move for knots or the Young-Baxter equation. Okay, you will see more examples and more explanations. And actually, The main theorem to support this main principle is that any good property on k particles in R2 induces a homomorphism from the pure braid group on n strands to the group G and K. So here we mean a good property on K part. Oh, excuse me. It may be maybe there is a confusion. So uh, mm, uh, so I mean that the total number of particles is n, and n is greater than k, and the good property depends on k particles. Okay. And the two examples will come immediately. And when I restrict myself to pure braid groups, actually, the map I'm going to define will be well defined for any braid groups, for any braid. But in order to have a homomorphism, I will need I will need to keep track of indices. So in order to have the product mapped to the product, I will keep track of indices, and that's why I have to require my braid to be pure. Otherwise, we may consider some homomorphism from the whole braid group to some free product with braid groups with of G and K with some permutations. But now, of course, here when I talk about good properties, first of all, I mean those good properties for 3 points on the line and for 4 points on the circle or line. So actually, here you have a rule how to write down a word. And the theorem means that if we take isotopic braids, then the corresponding words will give the same element in the group. Okay. And the main idea of the proof, not only of this theorem, but also of many other theorems supporting this principle and written in the book, is as follows. Codimension 1 properties correspond to generators, and codimension 2 properties correspond to relations. So assume we have some topological space. And this topological space has walls and has chambers. And we want to walk from one point of the topological space to another point. And when we walk, generically we cross walls, A, B, C, D, and so on. So we can write down a word. And if we have some homotopic paths, then we can go around a corner. And so a wall is something of codimension 1, and a corner is something of codimension 2. And so in many, many situations described by my main principle, uh, uh, walls correspond to generators of G and K, and corners correspond to relations. Uh, in particular, if I uh, if I talk about GN3 and GN4, the situation is as follows. Mm. So my codimension 1 property is, for example, 3 points are on the line. So this is codimension 1. This may happen for a braid uh, generically several times. But what are codimension 2 properties? Well, first, it may happen that I have a quadruple of points. A quadruple in a braid is non-stable. But if I perturb this quadruple, I can get 4 triples. and triples are stable. But if I perturb this quadruple in the opposite direction, I will have the same four triples in the opposite direction. And that's where the relation comes from. Also, the far commutativity relation can be treated as follows. So assume I have, for example, points 1 to 3 and points 1, 4, 5. So 2, 3 are on the same line and 4, 5 are on the same line. And here one can travel this way or one can travel this way. So the intersection between 2 and 3, between 1 to, so 1 to 3 on the same line and 1, 4, 5 on the same line. So these are independent events and they commute. And finally, the relation that we have something, we have involutions can be treated as follows. So if we have 2 and 3 on a line, and if we have some non-generic situation when when the trajectory of 1 is tangent to this line, this is not generic, and we perturb it a little in one direction, we have nothing, and we perturb it in another direction, we have one generator twice. So, and actually one can easily check that all codimension 2 events are like this. Mm, uh, mm, uh, to be non-stable, well, in different situations it means different things, and it's written in my papers. But here I give many examples. So I would say stables with respect to trisecants, triples of points, or stable with respect to quadruples of points. Well, you may ask me several questions. For example, there was a question whether 1 to 3 and 1 to 3 to 1 are the same. And actually, you may ask whether 1 to 3 and 2, 1, 3 are the same. Well, I did it. Maybe I can say because I'm lazy, because I don't pay attention to the order of points on a line. But otherwise, I can say that the group GN3 is already good enough and powerful enough. And here, mm, if I pay attention to the order of 3 points, then I can fix on the point which is in the middle. So I can say that instead of just generators I, J, K, I have mm, I have I pay attention to the generator in the middle, IJK or JIK or IKJ. So I will have 3 times as much generators, and the relations will look literally the same. And actually, it can be checked rather easily that again we will have a homomorphism from the braid group to from the pure braid group to GN3 prime. And in this homomorphism, one can really check that the relations should go in this order. So, for example, if 1, 2, 3, 4 are on the line, then the order should be 1, 2, 3, 1, 2, 4, 1, 3, 4, and 2, 3, 4. So it's exactly like that. Okay? So this is a bit more precise, but already GN3 is powerful enough. Uh, well, and you may ask what to do with GN3 graphically, how to draw it, and actually what to do later, maybe with links or knots. And I can say that we may treat any generator as a chord connecting 3 points on I, J, and K. And then this chord can be split into 3 chords like this: IJ, IK, and JK. Or we can have chords with double indices IJ, IK, and JK, and I can write it like this. So what it means exactly is some homomorphisms from GN3 to some GN3 prime, maybe to some GN capital 2. I don't want to decipher it here, but actually there are lots of homomorphisms from these groups. And actually, this has something to do with chord diagrams. Well, in fact, when we consider usual knot theory, what we are interested in when we look at a knot in 3 space. So usually we draw a knot like this, and in this drawing, we pay attention to crossings. And what is a crossing? A crossing is a situation when 2 points lie on the same line which is parallel to OZ. So, or maybe OY. So we have a family of lines, and if there is a point passing through 2 points which is parallel to a line, then this will be a crossing. So this approach to knot theory makes all knot theory combinatorial. So we may say, okay, a knot is an equivalence class of knot diagrams modular Reidemeister moves. But if we look at knots just from this combinatorial point of move of a combinatorial point of view, then some geometrical aspects of knot theory are not visible. For example, if we have a non-trivial knot in 3 space, then for this non-trivial knot, there is a non-trivial quadrisecant, a line which passes through this knot 4 times. And instead of just pairs of points, so that a line passes through the pair of points, I can suggest the following. I can suggest a horizontal trisecant. So if I have a knot in 3 space, I can look at those lines which pass through 3 points of a knot. And this line has to be horizontal. So it has to be horizontal, parallel to the horizontal plane. So in some sense, standard knot theory is a sub-theory of this approach. Why? Well, because if we have a knot in 3 space, then we can assume that we have some infinite, some infinite strand, maybe called I, which is far away from a knot. Then we may look for trisecants between 1 point on this I and 2 points on some other strands J and K. And those trisecants will be just horizontal horizontal crossings. So from this eye, we will have a screen, maybe not quite screen, but not quite planar screen, but cylindrical screen or something like that. No, if it's infinite, then this will be just a screen. And usual crossings will be such crossings with an infinite line. But then for knots, we can use not only such trisecants, but what we can use arbitrary trisecants. And what I did for braids, the generators of my groups were exactly what I'm doing now. And today I will tell how to pass from braids to knots, maybe how to pass from braids to links, what problems we have, and so on. So this is the geometrical picture, and here is yet another picture. So again, if we have a knot here, then just crossings for points correspond to the screen when we have a vertical line. And actually, Reidemeister moves will appear here. So if I move this knot and look only at those triple crossings which contain this vertical line, then we will have Reidemeister moves on this screen. But besides Rider-Master moves, there will be some other moves. And actually, there is something hidden, and I'm afraid I made a mistake here. I made a mistake here in this picture. So you see, how does the Rider-Master move look here? The Rider-Master move looks like this. So we have three strands, 1, 2, and 3. And we have a cross, and this is 1, 2, and 3. And we have three crossings, 1, 2, 1, 3, and 2, 3. So this is the standard Rider-Master move for knots. Of course, we have to say who is over, who is under, but so far I don't care. So this is the Rider-Master move. At the level of chord diagrams, this looks as what is drawn here. Okay, so this is how Rider-Master move looks like. But this is what happens for only those triseconds which pass through this infinite line. So these are not just 1, 2, but maybe infinity 1, 2, infinity 2, 3, and infinity 1, 3. But also we have the chord 1, 2, 3, and I made a mistake here. So there should be one triple chord like this. So if I add this information, this will contain more information than just crossings. So we will lose nothing and we will get more. Okay. Do we have other examples besides GN3 and GN4? Of course, we have GN4, and do we have examples which are not good or nice? So you may ask what is not nice and what does it mean a property is not governed by k points. Well, we can assume a motion of points in the free space. And there is a codimension one property is that 4 points belong to the same plane. Well, as the usual GN3 property studies usual braids. So then this approach should somehow give us a homomorphism from braids in R3, to GN4. But you see, there are no braids in R3. There are only permutations. Every knot in every knot in R4 can be unknotted. And if we look at some one-dimensional picture dynamically in so this will give us a picture in 4 space. And there are no braids. So a priori, there will be no interest in theory. And a posteriori, this property is not nice. What does it mean? Well, this actually means that there will be one more very unpleasant codimension one property, namely, if 3 points are collinear, for example, ijk, then whatever L I take, then ijkl will be coplanar. And this will give me a lot of new commutativity and a lot of new relations. So this will not be GN4. This will be something else. However, there is a way to overcome this problem. And actually, we can consider the situation when no 3 points are generic. So in R4, in R3, we consider the situation when no 3 points are collinear, but we take care of points which are on the same plane. And then it gives us a homomorphism from GN4 to from this fundamental group of the configuration space to GN4. And a very similar techniques works for the k minus one dimensional space. So for R k minus one with some restrictions, we get a homomorphism to G and K. So we have lots of examples. Now in my formulation, I said particles. Why didn't I say just points? We can do the following trick. We can use a projective duality. Yeah, everything I said about the Euclidean space can be said about the real projective space. So, for example, if I live in RP2, then instead of points, by duality, I can consider lines, projective lines. And instead of the property 3 points are collinear, I can say projective lines, 3 projective lines pass through a point. You may say, well, there is nothing interesting. This is just a projective duality. And there is no new example. However, instead of considering lines, which are the same as points from the projective duality point of view, we can consider curves, which have the same genericity condition, so which behave in some sense like lines. And curves form an infinite dimensional space, but there is still some codimension one property, and we can study those infinite dimension space by G and K. And actually, it works for RPK minus one when we consider hyperplanes, and we can even study some submanifolds inside manifolds and many other things, and it's written in my book. Okay, well, other good properties on two manifolds? Well, this is another story. I can just say that if we are on the torus, we should be very, very careful because there is more than one geodesic passing through 2 points and more than one circle passing through three points. I don't want to stop on this slide. And there is one more example for further research, which I just gave to my new student, Yaroslav. So instead of configurations of points in R3, which will give me GN4, I can consider configuration or points or dually hyperplanes. I can consider configuration of lines. So I can say, okay, assume I have R3 and I have a configuration of lines. And I can look at this configuration of lines from 2 points of view. So first of all, I can try to classify this configuration of lines. This is a very well-known problem. And of course, it's completely solvable, but it has relations to algebraic geometry. How to solve this problem? There are many other problems. I can draw a picture with quasi-lines and ask whether this picture can be realized by lines. And so I can consider those lines up to isotopy. Or I can consider any quasi-line as a motion of points. I can do it in space or in the projective space. And of course, you can imagine the same thing in higher dimensions. So you can formulate lots of problems, and this is a new direction of research. Well, now the thing I'm going to struggle for will be links and braids. Before I talk about links and braids, I can assume that there will be questions like that. So first, there is a map from one group to another group. About the target group, G and K, is the word problem solvable? Is the conjugacy problem solvable? Why are those groups good? So concerning the last question, why those groups G and K are good, so actually there are lots of homomorphism, and I think I will mention them during the rest of my talk. lots of homomorphisms from G and K, not only G and 3, but also G and 2 and so on, to Z2 star Z2. So this is the free product of many copies of Z2. So you see the group on the right side is powerful enough. It has exponential growth. On the other hand, it's very easy to deal with. Here, the word problem is solvable. So this means that we can get easily invariants easy to compare and powerful enough. On the other hand, as for the word problem in G and K, it is solved in very, very partial cases, and this is a challenging question. So for G and 2, yes. For GK plus 1K, yes, in many cases. And it seems like for G5, 3, yes. And other things are more complicated, and for the conjugacy problem, less is known. There is also um, other some properties G and K, and um, yes, for R RK minus 1. So for R2, 3 points on the same line. For R4, 4 points on the same plane. For R5, 5 points on the same hyperplane, and so on. Yes. And also one more thing, since one more thing I think I forgot to mention is that since everyone knows from school that there is such an equality for chosen K, there is a simple way to extract two groups from G and K. So actually, there are homomorphisms from G and K to G and minus 1K plus 1 minus 1K, and G and K plus 1, G and minus 1, K minus 1. Actually, those homomorphisms are as follows. Here I have indices A, 1, 2, and so on, K. And I can fix one index, for example, N. And if I want to have this, I can fix only on those tuples of indices which do not contain N. And I will get a map like this. And as for that, I can use for those tuples of indices which do contain N. And then I just forget this N and get K minus 1 remaining indices. So there are lots of homomorphisms, and actually there are lots of other structures on G and K I'm not talking about today. And now, one more question I can imagine you ask is for those PBN 2G and 3, is this map isomorphic? Is it epimorph? Is it onto, or does it have kernel? And the answer is neither of those. So first, it is by no means onto, because really GN3 is much richer. So the words you can write in GN3 much more are contain much more structure than those we can originate from braids. This, if some of you knows virtual braids, so this is like virtual braids are more powerful than classical ones. And yes, and the question is whether there is a kernel. Well, I can give you an obvious kernel, and this obvious kernel is as follows. If we have n points on the plane, so that none of them is, no three of them are on the line, then we can rotate them by 360 degrees, a full revolution, and none of them will be on the same line. This braid is non-trivial, and this is exactly the generator of the kernel, the generator of the center of the free braid group. And I expect that this kernel is exactly the center of the pure braid group. And this is almost proved, but I believe this is true. But well, if it's so, then this is almost a homomorphism. A verb bit has to be fixed. Well, now I want to pass to links or knots. What is the problem with links or knots? So first, if I consider a knot in 3 space, and I want to scan this knot from the top to the bottom, then when I scan it by planes, two unpleasant situations may happen. The number of points changes. And also, there is no standard way to enumerate strands, right? And that's why we can consider links on knots on links as equivalence classes of braids modulo Markov moves. So we have braids, and we take their closures. And the closure of a braid gives us a link. And there is a famous Markov theorem which says that two braids have the same closure if they're obtained from one another by a sequence of the following moves. So first, if we conjugate one braid by something, then this something can be cancelled if we pass to the closure. And the second Markov move is that if we take an n-strand braid and add another generator, positive or negative like that, and close it up, then the closure of this braid will be isotopic to the closure of the initial one. So then we may expect to have a chance to get an invariant of knots. But still, an invariant of knots or links where? For example, if we have a knot, then the number of strands can be arbitrarily big. So how to get a knot invariant here? So in G5, 3, in G6, 3, in G7, 3, and so on. So that's a question. So maybe one clue to that question can be related to chord diagrams. So you see here, if we look at trisecant where we have strands number I, J, and K, then we can put such a triple chord diagram and we can do some tricks with that. I'm not going to talk into details with those tricks. And then I can forget about indices. I can say my trisecant is here. So it connects those 3 points. And if I say here and those, then I will have some chord diagrams, modular moves, but those will be not just usual chord diagrams. Those will be triple chord diagrams. And this is an interesting phenomenon. So this is what we are working on. This is an ongoing project. But now I will be talking about links. So here one problem comes into play. So links are somehow better than knots because of the following reasons. And so this is a joint work with Igor Nikonov. Braids are better than knot in the following sense. No, links are better than knots in the following sense. We have mm, numbers which are given from the very beginning. So, for example, we can have blue strands, we can have red strands, um, we can have green strands. So mm, some number of strands of each type. So we can have such a braid. And then we can say, okay, blue strands are number one, red strands are number two, green strands are number three. And try to get G and K properties like 1, 2, 3. But you see here we get into a trouble because if we scan our knot by a plane, then there will be many blue points, many red points, and many green points. And for example, if I want to have a trisecant, which is denoted by 1, 2, 3, there will be many trisecants like that. And if I look at a concrete point 1, there can be one trisecant passing through 1 to 3 and another one passing through 1 to 4 independently. And so if I'm very uncareful, then it may happen that I will have 1 to 3 and 1 to 4 to commute. And if everything commutes, well, nothing is left. So all the beauty of my groups G and 4 will disappear. Then how do we solve this problem? Well, actually, the idea of my work with Igor Nikonov is as follows. I consider a braid on n strands, um, uh, small n strands, like here. So here we have a three strands, and I close it by three additional strands, which are vertical. So this is a standard closure of a braid. So three initial strands and three additional strands. So the number of components. Excuse me. No. N capital is the number of strands, and small is the number of components of a link. So to have a three-component link, I may need 10 strands. So then in total, there will be 20 strands, 10 of them representing the braid itself, and 10 vertical ones. And then I say that my braid that my link is an equivalence class of braids modulo Markov moves. And then I will construct some algebraic thing which will be invariant under two Markov moves. And this will be what we're doing now with Igor Nikonov. Well, after that, something is going on with knots. I will not get into detail about that work. And this is what is wrong. What is wrong in general case? I just mentioned that there are many points 1, 2, and 3. So this is what I already said. And actually, the main idea is to pick some points of color 1, some point of color 1, some point of color 2, and some point of color 3 to have a unique trisecant of color A1 to 3. And how to pick? Well, we can take all possibilities and then sum over all possibilities. So you see, if we have three green strands and three red strands, we can choose one red one and one green one. Plus, we have, for example, one blue one. So we can choose them. And also, we have to take care about those vertical strands. They are also green, blue, and red. And actually, when we choose, we can choose, I would say, positive ones, which are those coming from the braid itself, and negative ones, which are coming from the closure. So there is, there are various ways to choose. And then, roughly speaking, the idea is to sum up something. And well, what is mentioned here is a homomorphism from the braid group to some um, which are braids which are not pure, to some free product with GN3. We just take care about endpoints. And this part, which is rather technical, is written by Igor Nikonov. And the idea to take the idea is to take some map from the braid group, and this map is just a, sum where we take uh, all choices of components of different colors, and then we take this maps. I would say it is phi. So phi is roughly speaking is the GN3. So when we have a choice of component for a braid beta, we call the resulting braid beta tilde. So we take this GN3 thing like that. But then we have to take a quotient by something. What sort of quotient do we have to take? So here we see some combinations, projections, and so on. So first of all, where is it valued? Where is this invariant valued? It is valued in some formal linear combinations of something like uh, uh, mm, uh, I would say uh, some groups. So roughly speaking, if we have a good group, maybe free group, then we can say, okay, we have elements of those groups and make a basis uh, generated by that elements, and make a basis and consider the free module generated by Z. So we formally take a sum of those elements with positive and negative coefficients, but not quite group elements, but I would say group conjugacy classes. And actually not quite group conjugacy classes, but something more. So I don't want to make you boring, but I just tell you a couple of details, so what can we expect from the first Markov move, and what can we expect from the second Markov move? So first of all, if we conjugate a braid somewhere here, uh, then the GN3 invariant of that braid will get conjugated. So this map phi to GN3 will get conjugated. And actually, if we were dealing with mm, just GN3 invariants, Mm, if we are dealing with just closed braids or braids inside the cylinder, the theory will be very easy. As braids are mapped to GN3, uh, uh, closed braids are mapped to GN4. Excuse me, to conjugacy classes of GN3. And the same about GN4. And since these groups are good enough, and there are maps to free products of Z2s, we will get lots of nice invariants. But the second Markov move spoils the situation. So actually, here we choose different components, And that's where we get a conjugation from the first Markov move. Now, what about the second Markov move? So if we have one braid here, um, if we have one braid here and we take a conjugation, a stabilization of this braid, we should remember that behind that braid, we have vertical components. We have vertical components behind this braid, and we can choose our initial components positively, and we can choose our closing components negatively. And the additional component, like here, is very much similar to that vertical component. And uh, also, it's of the same color as the component it is closing. So here what we pretend is that these two components, that this one and that one, will have the same mm, will have the same impact with opposite sides. So that's why we have to take linear combination. That's why we have to take conjugation, and that's why we have to take some factorization. So this is some factorization. This is some color change maybe, and we get an invariant. And actually, this invariant is not very powerful. It's a link homotopy invariant because it doesn't feel crossings, self-crossings, crossings between strands becoming to the same component. I'm really interested into crossings IJK, but I'm not interested in crossings IIJ. That's why such a crossing change within one component doesn't give me a result. That doesn't change my invariant. So okay, so this is what is constructed, and actually this is how it's proved. It's formal. It's formal proof. It's a formal proof that for the first Markov move we have some conjugation, and roughly speaking, this means that conjugated elements, basis elements, go to zero. And for the second Markov move, so actually we just look at two last strands and they are cancelled. Well, actually, there are much more questions than answers here. So first of all, we completed only one piece for uh, mm, links, not for nodes, but I want to tell you one more very important story, and that story is called a map from classical objects to virtual objects. So I'm asking whether the audience here is familiar with virtual node theory. Well, roughly speaking, virtual knots can be thought of as knots in thickened surfaces. So we can consider thickened surfaces, and we can consider knots in thickened surfaces, and they can be drawn on the plane by embedded graphs. And this theory was introduced by Lou Kaufman in around maybe 1988 or so. And actually, what you should know that virtual knots have extremely powerful invariants. Virtual knots mm, have invariants never seen in classical knot theory. For example, these invariants easily allow one to solve easily to detect knot invertibility. And also, there are lots of invariants which are valued in pictures, like combinations of linear linear combinations of knot diagrams, which is very good because it is much more than just mm, it is much more than just a polynomial or a number or a group. We have a whole diagram as an invariant. And actually, there is one project we are working on, which is as follows. We can take, we want to map the classical world. So, for example, classical braids, knots, links, and maybe manifolds to the virtual world. And if we perform this project, then whatever invariants I have, and I have lots of, and many of them are given in my book, will go back. So if I have nice maps in this direction, then the invariants will go back. I take the full pullback. And now I can tell you that for braids, this is already done, and this allows one to extend Kaufman brackets, Khovanov homology, Burau representations, and many things for braids. And the idea is very easy. So if we have an n-strand braid, then we can delete one strand and consider the remaining n minus one strand as follows. When we delete one strand, we can think of it as being the axis of a cylinder. So we delete this strand, and now the rest is projected to a cylinder. And now we can draw a knot diagram on the cylinder. And then actually, I have something in the pocket that knots in the cylinder can be mapped to something virtual. And so we can extract invariants from the left. And now we may try to get invariants of virtual knots. For braids, it works perfectly. For knots, there are some issues to overcome. And maybe you can see here a relation with what I was talking before. Because you see, if I have a braid, I can look at crossings of this braid, right? So this is just a crossing. This is just a crossing made by two strands. But if I take one vertical strand and make a cylinder, then all those crossings on the cylinder are just projections from this strand. So somehow I use this trisecant theory. I use this theory where where instead of just double lines, I take triple lines. And this gives me much more. But if I have a knot, not a braid, then the question is which strand to take. So actually for a knot, we don't have an obvious axis to project from. Do we say that virtual knots have a greater number of invariants of classical knots? Yes, much more. Uh, uh, so there are whole books. I can send you my books. Just write me an email. So, for example, there is a projection from So, if two classical knots are equivalent as virtual, then they are equivalent as classical. Lots of classical knot invariants are extended to virtual knots, including quandles and Chobanov homology and many others. But since virtual knots live in two surfaces have non-trivial homotopy. And this non-trivial homotopy has something to do with free groups. Well, maybe not free groups, but rich groups and pictures. So we can draw a picture, and this is very important. But actually, virtual knot theory contains classical knot theory as a proper part. Well, and now some more things about G and K. Maybe there is some hierarchy. So in principle, our usual braid group when we deal with standard crossings is spiritually GNK, GN2, because if we consider a braid and want to draw a picture of this braid, so what is a crossing? A crossing is a situation when 2 points have the same x coordinate. So if we consider points as complex numbers, then it means that the real part of their difference is 0. And then if we extend it somehow, so if we add some information about who is over, who is under, who is closer to us, who is far away from us, then we get an enhanced GN2 theory. So the standard arting representation is GN2-like representation. Then our 3 points, if they're collinear, this means that the ratio of the two differences is real, okay? And if 4 points are on the same line or on the same circle, then their cross ratio is not integer, of course, not integer, real. And maybe we can ask what's next. Maybe there is some algebraic geometry. You may ask, well, through any 5 points, we can draw a conic, but there are some issues related to degenerate conics. But there are some problems with algebraic geometry. And actually, when we look for good properties, nice properties depending on points, we may take into account not only topology, but also maybe algebraic geometry. So if we have, say, an elliptic curve, why can't we take into account the way of summing points, the summation of points? So we can imagine many things. So the more structure our surface or our manifold has, the more we can expect from our GNK. Many things, many examples are written in my book with Nikonov, Fedoseev, and Kim. And yes, and this is actually a calculation of what we should have for a knot. A potential invariant, but there are actually some problems in collecting this invariant in a good way. So in some sense, if we consider such a diagram of a trefoil, two-strand braid, and close it up by 2 vertical strands, then we can assume that 2 pairs of points originate from the top, and they start moving, forming a braid, and then we draw triple points. We look at trisecants. We look at those situations when 3 points are on the same line. So, for example, it may be that here A, B, and X are on the same line after some rotation. So A, B, and Y are on the same line. And we can look at that from the point of view of A, from the point of view of B, and we get several chord diagrams. And then the question is what to do with those chord diagrams. So that's a problem. That's still a work in progress. And then maybe we will get something like linear combinations of chord diagrams modulo moves. But those chord diagrams are much more complicated than usual knot chord diagrams, usual Gauss diagrams we know, because they have to do with triple crossings. Well, of course, GN4 theory can remind us about quadruple crossings, and this will be much richer. But the GN3 theory is still not completed, so we still have to work a lot with GN3. Well, also functoriality, cobordisms, and two knots. Well, roughly speaking, everything here is functorial. So if we have two braids, one braid on the top and the other braid on the bottom, uh, we can see how a trisequence change, and we can see how it goes. And uh, actually, one can expect that this should give an invariant of two knots. But this is just a project. Well, and here some list of unsolved problems. So one problem which I still mention as a solved is getting knot invariants. So as for link invariants, this is done. But this is done only for a link homotopy because, as I mentioned, it doesn't feel uh, this crossing change. Uh, mm, Also, as for node diagram, it's still a project, ongoing project. And here, some group gamma and k mentioned. You can forget about that, but there are some other tricks, some other fancy groups, and again, lots of nice fundamental groups of configuration spaces can be mapped to gamma and k. Well, then we may play the game of G and K hierarchies. For example, GN2 vertical lines, GN3 arbitrary lines, GN4 circles, and what's next? What other things can we get here? Generalized to algebraic geometry. So as I mentioned, we can consider not only lines or planes or hyperplanes, we can consider manifolds and submanifolds which move somehow. Well, there is a question about non-integrable codimension one property. What do I mean by non-integrable? So roughly speaking, when talking about points on the plane, I always say that there is some fixed number of curves. So for example, there are lines. There are lines and that's it. And 3 points satisfy my good uh, uh, three property if they are on the same line. But maybe there are properties of points which somehow do not belong to the same fixed number of lines, which are trickier. I don't know. Well, and the same about circles. Uh, well, recognizing smooth structures, well, it's very far from, uh, well, it's maybe a dream because it's not done yet done for knots. But principally, we can do it manifolds. Well, also tropical GNK theory. Well, if there are some good students, I can tell a lot about tropical geometry and other things, and also how can it be used for enumerative algebraic geometry. Again, I can tell it separately. Also, further directions, again, unsolved problems and so on, not invertibility. Well, in the virtual world, there are lots of invariants easy to work with, which detect not invertibility, detect in rather an easy way. And if we have a way of writing down a word from a knot, then and this word is manifest somehow. If it manifests, for example, knot invertibility, then we can say, okay, a knot whose word is not palindromic is not invertible. Of course, maybe it will not be a knot. Maybe it will be a picture, which is not symmetric. Maybe it will be a linear combination, which is not symmetric in some sense. But if we manage to do something either through G and K or through virtual knots, then we may get knot invertibility. Upgrade Kaufman bracket to virtual one, to picture valued one. Everything is done for braids, but for knots, well, not quite. There is some issue of closure, but again, what is a Kaufman bracket? A Kaufman bracket is something where we have such a skein relation, so we can smooth a crossing. But we should remember that any crossing originates from a triple crossing when we look from some other strand. So this encourages us to think about horizontal trisecants, and maybe we can look for some skein theory for trisecants, not for mm, just knots. Upgrade Hovanov homology theory. Well, it's natural. For braids, everything works well. And actually, for virtual knots, Hovanov homology is made much stronger than, much stronger than for classical knots. For braids, everything works perfectly. For knots, not quite. Why did I mention Vassily invariants here and Kontsevich integral? Well, you see, Kontsevich integral is, in a sense, a way of scanning a knot. So if you know this issue, so you start scanning, you take a Morse knot in R3 and you scan it by horizontal lines, and you take some chords here. And I'm interested in what can happen if we look at triple chords. Maybe we will be able to draw a triple chord diagram here. And maybe this will be related to our invariants. Well, such dream, which is far away, is if we do this theory for knots, we should be able to do it for three manifolds. But this is again a dream. Well, I think I don't have a list of references here. Something was in trouble with my file, but I can send it separately to everyone interested. And also, I can mention that we have a research group called Maps from Virtual Notes to from Classical Notes to Virtual Notes, and so this is a very international group which contains lots of people and students. And Kaufman himself is very interested in that ongoing project, and we have lots of projects for students. So maybe I'd like to stop here.
Thank you very much, Vasily Olegovich. So, any questions or comments?
I see something on the chat. Mm, uh, uh, mm, so are there any common properties of, yes, I answered this question. Do we say that virtual knots have a greater number of invariants? Of course, much greater. Um, uh, how can we this way get corresponding invariants of knots through homomorphism? Homomorphisms of what? There are there are lots of virtual knots which are classical. There are lots of invariants for example, uh, mm, vanish on classical knots. For example, one can write down a tricky Alexander matrix, and this matrix will have determinant zero for classical knots and not for versions. Uh, mm, so there are lots of invariants which are complete for classical and not complete for virtual. So there are lots of invariants of various sort. Um, uh, Yeah, so as for email, just write me in email. So I leave it here. And if you wish, you can join our group. And we have three seminars Monday, Wednesday, Saturday, and we have a lot of activity here. Yes, maybe you have more questions than those I saw on the chat.
Any more questions or comments? Maybe I will ask one question. Is the group that you introduced GNK, does it have any relation with Drinfeld's Grothendieck-Teichmüller group?
Uh, I don't know. Uh, mm, mm, Dreamfeld's Grothendieck type.
Uh, uh, Drinfeld, basically, it's like absolute Galiba group kind of thing.
Frankly speaking, I don't know. Yes, one more thing to mention is, of course, one can look at there is a whole story. There are lots of questions about what are representations of G and K, matrix representations, and not much is known, but it is known that my G and K are related to uh, Coxter groups. Greenfield, so if you can send me by email, if you can repeat your question by email with more references, I can look at this more carefully.
Thank you. Any more questions or comments?
So thank you very much.
So let's thank our speaker once more.
Ben çok memnun oldum. Çok teşekkür ederim.
Biz çok teşekkür ederiz. Hem sizin Türkçeniz çok etkileyici, onu söyleyeyim size. Mükemmel bir Türkçeniz var.
Oh, oh,
So
ah,
I will,
ah. Yeah, yeah.
uh,
Okay.
uh,
Thank you very much. Güle güle.
yeah. So I will stop here the recording.
Okay.